and it's tradition for me to have my face on here at least once. So hello, I'm David. If you haven't met me, what have you been doing with your life? I'm the coordinator of the Maths Learning Centre, and this is a revision seminar for Engineering Maths IIB in 2019 semester 2. As I've said in all the revision seminars today, it's freaking me out a bit that it's 2020 next year, and we're nearly at the end of 2019. So anyway, I'll be fine. And this course is going to be different next year. So this is the last year that they're doing Engineering Maths IIB. Next year they're cutting it up and putting it into... They're doing a bit of musical chairs with the topics and making new courses. Yes. So next year the Laplace Transforms will be over in the other course that has differential equations in it, which makes sense. Yeah?
Does that mean if you fail, do you just not take it again?
I have no idea what the rules are. I'm sure they're in the midst of figuring out the rules of what will happen if you don't pass this course. Presumably, no idea. I'm sorry. I've just been informed last week about the new plans. Right. The first thing I want to say is that on your webpage for Engineering Maths IIB, and there was a link in the email that told you that this was on today, there is revision seminars from the past, and I'm extremely happy with the one I did in semester 1 this year for a different course called Multivariable and Complex Calculus. It has most of the same content, it just doesn't have the Laplace transforms. And I talked about integrals in multivariable calculus, and the 11 or 9 or so different kinds of integrals in this course, and in the other course, and how they're related to each other, and which theorems allow you to calculate them. I was really proud of that one. So if I don't get to integrals, then you can go look at that. But I'll still probably talk about some integral stuff because I don't know if the rest is enough stuff to talk about for 2 hours. But really proud of that one, and you can see me doing all sorts of things with Play-Doh and string and stuff. So with models of the 3D shapes. So cool. All right. So I will talk about the Laplace stuff first. That's on the table on the board here, and. The only two that are Laplace things are the convolution and solving PDEs. So luckily, see, I never studied differential equations as a student. I learned everything I know about differential equations from helping students in the Maths Learning Centre. So luckily I have someone's notes. Thank you. Okay. So my understanding of Laplace transforms is that this magical thing that will turn a function into some other function and has the property that derivatives are the same as... I always forget. Just a second. Derivatives are the same as... Just a moment. Derivatives are the same as, where is it? Here it is. Multiplying by s. Awesome. Okay. I always forget it's multiplying or dividing by s. As you can see, I only do this once a year, so it takes me a little while. Maths 1B, I do 3 times a year. I'm much better at Maths 1B. So if you did Maths 1B 3 times in a row, you would be better at it too, I'm sure. So that's why they're so useful, because they turn derivatives into multiplication. Similar to way back in the day when logs were invented, logs were able to turn multiplication into addition. Now we have this fabulous thing that turns derivatives into multiplication, and that makes things a little easier. And particularly, it makes things like solving differential equations easier. Doesn't make them easy, just easier. So, right. So this is the table that the lecturer gave in the exam last year, well, in 2017 actually, and I'm presuming that you're going to get a similar one in your exam, and it has the classic transforms of specific functions and what their Laplace transform is, and then it has all these different theorems about how different things that you can do to functions relate to what you can do, what you have to do to their Laplace transform. Okay. So I'm not going to go through all the details of Laplace transforms, but what I am going to do is I'm going to just organize this by that idea, because that's where the convolution comes in. So the idea is that your function can go back and forth between the Laplace transform of the function, and it's tradition to use a capital letter for the Laplace transform and a small letter for the original function, and it's traditional for this to be a function of t and this to be a function of s. Okay. All right. And the idea is that things that we do to functions relate to stuff to do to their transform. So it's similar to when you first learned about the square root, and well, maybe not when you first learned, but later on at some point when you learned about the square root, you went, all right, how does the square root interact with plus? How does it interact with times? How does it interact with divide? How does it interact with powers? They're the sorts of things we want to know. And so that's what we're going to do here. I'm going to say stuff to do to functions, and what does it do to the Laplace transform. So the first thing that it does is that if you multiply your constant by function by a constant, it multiplies the Laplace transform by a constant. So if f went to f, then AF goes to AF. Nice, for A being a constant. And if f goes to f and g goes to g, then f plus g goes to f plus g. It's lovely. It's beautiful. It's the thing that we hope for all things. You'll have to remind me to keep pushing the paper up. After so far 4 and a bit hours of doing this, I still haven't remembered to put it up every time. So, okay. So that's the addition rules, and on the Laplace transform table on the computer, it's here. Linearity. That's what linearity is. If you add stuff, it adds them. If you multiply them by stuff, it multiplies them. Okay. Which is exactly how integrals work, it's exactly how derivatives work. We're used to that. The next thing is that why they're so useful is that there are some things you can do to functions that make the Laplace transforms really useful, which is derivatives. But I'll get to that in a second, because now I'm going to talk about convolution, because see here we've got multiplying the Laplace transform by a constant, and we've got adding the Laplace transforms together. It would be useful to know how Laplace transforms interact with multiplication. That's something that's a useful thing to do. And unfortunately, it's not very nice. So we're going to have to do a bit of jiggery-pokery. So that's the big question. How does it interact with multiplication? It's a good question. So we do know one thing. Most of the things we know about how it interacts with multiplication are to do with how it interacts with multiplying on the Laplace transform side and what that looks back on the function side. We actually don't really know what it does when you multiply two functions together on this side, but we do know what it does if you multiply functions together on this side. So we're just going to have to do it backwards, unfortunately. It's not nearly as nice as we would like. So this is the rule. So f times g on this side goes with f star g on this side, and this is called convolution. And we all say, what the hell is convolution? And the smug answer would be, well, it's what you get when you do multiplication on the Laplace Transform side. It occurs to me that the name of this probably means it existed before Laplace Transforms. Otherwise, it would have a more Laplace Transformy name. And I have a feeling it existed first, but most people only see it when they do Laplace Transforms. That's the only time I've seen it. I'm pretty sure it occurs in some probability theory stuff as well. But you know, you're not going to do any of that, so we'll skip that. Well, that's what we want to do. We want to figure out what multiplying here does over this side. So we need to figure out what this convolution is. And there is a definition of that. And the definition is that f star g of t is the integral from 0 to t of f of tau g of t minus tau d tau. Or it could work just as well. It doesn't matter which way around it is. You can switch the f and the g and it's still the same. Which seems like a really weird-ass thing to do to a function, pair of functions. I mean, as far as I can tell, I mean, let's just look closer at this. What we've done is we've taken f and we've multiplied it by g, but g is running backwards because it's got a minus tau instead of a plus tau. And then we multiplied them together and integrated that. And the answer for this is the running value of this integral. As t moves forward, you keep calculating the integral further and further, and that's what the function is. It's weird. So I would be really interested to know a little more about this thing. Let me just see if I can get a handle on this. So if this is f, and this is g, all right, I've done one sparky and one round so I can tell which one is which. Then what the hell? So this would be the tau axis here, and doesn't matter whether it's the tau or the t, I'm just doing this thing here. And then this is what g would normally be. It's normally in terms of t. And then what we do is we do f of tau, which is not different. That's the same. And we go g of t minus tau. Okay, so here's the thing. This is still a function of tau now. The t is a constant because it's up here as a constant. And the term, so t minus tau is how far tau is from t. When you subtract things, it's the distance between them. So if you pick a specific value of t, right, and let's say this is 0 here, then g of t minus t would be g of 0, which would be what this point is. And then g of, like if the tau was t plus 1, if the tau was t plus 1, then that would be g of t minus t plus 1, which would be minus 1. Oh, crap. That doesn't make any sense. So if we go back, if we go forwards to t minus 1, oh, okay. So it runs the function backwards from this point. Got it. So g of t minus tau runs the function backwards from the point t. So you take this function, you put it this way, starting at point t, going backwards. And then what you do is you multiply these functions together. Every function value here multiplies by every function value here. You multiply them all together, and then you integrate that from 0 to t. Yeah. Yeah. Great. Okay. So then you have f of t, which is whatever the hell it looks like. Well, over here would get... And there wouldn't be anything here, would there? Nope, don't get it. Just a second. This is my first try to actually try to understand these things. Most people go, yeah, just tell me what to do. But I really want to try. So we do the integral from 0 to t of f of... Now this isn't going to have a tau here. Let's do x, because there's no tau in Desmos. There you go. That's the convolution. What is that? Sure. And why not? So that's g of x there, the blue one. And this, if t is 5, that's what g of t minus 5 is. It's running backwards. And if t is 0.8, that's what g of t minus 5 is. It's running backwards. And so... for each value of t, it's a different one, isn't it? Okay, got it. So... this says you pick a value of t, and then you make the function g of t minus x, and then you do the integral of that from 0 to t. Okay, right. So if t was 0, you would do, that's g of 0 minus x, which is perfectly backwards, and then you multiply that by f of x, and you do the integral from 0 up to 0, which is 0. And so you get 0. And then when t is 1, you do this function multiplied by the x plus 3, and you integrate that from 0 up to 1. And so you get this, whatever that area is. Just a second. Wow. I don't know if it's worth trying to understand this. Okay, right. Let's just ignore all of that. All right. So all of these functions... Oh, crap, wrong one. All of these functions, technically, when you do Laplace transforms, only start at 0. Why did that not do anything? There we go. Come on. So if I change this without the 3, that doesn't really do anything. Okay. No idea. It's some weird-ass thing that combines these two functions in this way. I have a feeling that there's going to be some special cases that when this convolution works out to something nice. For example, if everything is e to the power of stuff, I have a feeling it's going to work out to something good. If everything's e to the power of stuff, then other e to the power of stuff will happen. Okay, I made a really good attempt. Another year. You guys, it's too late. Well, it's not too late, you know. When's your exam? All right, well, you know, come to Maths Learning Centre, we can try and figure it out. Okay, so I could conceivably calculate the convolution of something, and I just want to do the calculation and see if I can get something. And I have this instinct that if it's e to the power of something, it's going to be something good. So let's just try it. Let's do those two and see what we get. So f star g of x is going to be the integral from 0 to t of e to the 3 tau e to the minus t minus tau d tau. So I've put tau into the first one, or tau, some people pronounce it tau, tau into the first one, and t minus tau into the other one, and multiplied them, and now I'm going to integrate that. But because they're both e to the power of, I can add them together, right? So that's actually 4 tau minus t. So I can integrate that now. So from tau equals 0 to t, e to the 4t, the t is a constant here because it's not the variable that I'm integrating against. And so that doesn't count. And then the derivative of this thing is a constant, so I can just divide by that constant along the way. And so that's equal to 1/4 e to the 4t minus t minus 1/4 e to the 4 times 0 minus t, which is e to the 3t minus... Ooh, that's interesting. Wow. Look at the original functions. They came back again. Huh. That's cool. Wow. I'm rather impressed by that. So there's probably some sort of fabulous rule with exponentials that you could probably prove that something along the lines of e to the ax, e to the bx comes out to e to the a, e to the, oh crap, they're supposed to be t's. Bloody hell. Now we're so used to using x for everything for the first, 8 years of our algebra experience, and then suddenly we're using t for everything. So there's probably some rule that says if you have AT and BT, then you'll get like A minus B. Like this is A minus B, and then you have the first one minus the second one. Okay, so that's what it is. It's not really particularly edifying to me, but that's what it is. That's how a convolution works. And I can imagine that if you do the convolution of a constant with something, then that might be a thing. I just want to try that too, just to be sure I know what's going on. Let's try this. Just want to see what happens. So when I do the convolution of these two... Oh, bloody hell. Thank you. When I do the convolution of these two, it should be... I'll run the first one. I'm just going to write it down. Got that right? Yep. Okay, so f is always 5 no matter what I put into it. And g is just what it is, just t, so I'll sub in t minus tau into that. And so the integral of that, the 5 will still be there. The integral of t will be t tau, because t is a constant, tau is the variable. And then this will be a half of tau squared. All right. Tau equals 0 to t. So we've got t times t minus a half of t squared minus 0, t times 0 minus a half of 0 squared. And so we've got 5 times t squared minus a half of t squared, which is just 5 times a half of t squared. Which is interesting because it's 5 times the integral of g. Oh, I reckon I don't know whether that would always work. But it's got to be the integral of something. Because the 5's there, it would just come out. The other bit would integrate. Oh, do you know what? I should have done it the other way round. Yes. Just let me do it quicker. You know, so the whole thing's slower because I've done it twice, of course, but you know. Like that, because it doesn't matter which one has the t minus tau or which one has the tau. And so then this is 5, and this is just tau, and it's just the integral now. Sweet. That's nice. It does come out the same either way. So it looks like if you're going to actually have to calculate an actual convolution, you want to choose the simplest function you can to be the one that you sub the t minus tau into. No, yes. Complicated ones, when you sub in the t minus tau, they'll just be horribly complicated. All right, nice. Feeling good. So it looks like this argument would totally work for anything. So it looks like if it's constant times something, then the convolution turns out to be the integral of the other thing. Okay, so convolution is some sort of weird-ass integral thing. Right, whatever. So what does this mean? What does this mean? This means that the Laplace transform so we know that the Laplace transform of the convolution of 5 and t is the Laplace transform of 5 times the Laplace transform of t. Convolution before transforming is the same as multiplication after. So when you do the Laplace transform of a constant, according to the table, 1 would become 1 over s, so this will be 5 lots of 1 over s. And the Laplace transform of t is 1 over s squared. And so that would be 5 over s cubed. Yay! Okay. Don't know if that helps. Let me just go back to the document camera. So that would be 5 over s times 1 over s squared, which is 5 over s cubed, if I wanted to figure out what the Laplace transform is. And I guess this could shortcut the whole convolution process, because now I could just untransform the 5 over s cubed, and that would tell me what the convolution is. So maybe one of the purposes of this is that maybe there are some situations when convolution is important, like in probability theory, and the quickest way to find the convolution is to go via the Laplace transform. Maybe that's what it's for. I don't know. Okay. I have yet to know why this is useful. So, are there any past exam questions or assignment questions about this that are worth doing? Yep. Don't read it out. That's ridiculous.
That's the question one.
Thank you. Okay. This is it here. No, not going to work. So we have f of s is 1 over s squared plus 4. Yep. And using the convolution theorem, expresses a convolution integral, and 2, evaluate it. To find f of t. All right, let's go. Rightio. Let's do it. Okay, so, well, the whole point of the convolution theorem is that if you multiply the transforms after, then it's the convolution before. So this is the product of two things, and it looks like 1 over s squared and 1 over s squared plus 4. So I'm going to make a wild guess that that's what we want to do. So f of s is okay. So those two things are multiplied. So that means it must be that's a product there, which means that before it was a convolution. So we should find the inverse transform of both of these things separately. Now 1 over s squared becomes t, and 1 over s squared plus 4, that's one of the sine or cos or something, isn't it? So according to my table, just let me switch to this for a second. According to my table, 1 over s squared plus thing squared is 1 over thing sine thing t. Okay, so mine was a 4 in this spot, so the omega must be 2. Okay, so what that means is we know that the Laplace transform of t convolution half of sine 2t must be the Laplace transform of the two things multiplied together. Right, that's how convolutions work. Multiplication in Laplace transform land, in S land, is convolution in T land. Okay, and so, right, cool. So I probably could have done it all with inverse Laplace transforms, but whatever. Okay, so therefore my f of t is this thing. Which is an integral. And they said to do it as a convolution integral, so I presume that's just write this as an integral. So 0 to t. So I'm going to have to choose which one's going to be t tau and which one's going to be t minus tau. Sorry? Yeah, put this one as a t minus tau. That's the simplest one. So, yeah, let's do that. Okay, so that's part I. Done. It's convolution integral. Which is distressing me only slightly because I'm going to have to do integration by parts. But, yeah. That's sad. Okay. Okay. So what's this? Because this is two things that both involve tau. So I do know if I differentiate this one, it'll go away. So I'll do that. So I want to differentiate this one, so it's going to have a dash. So it's going to be like that. So I want to differentiate this thing. I want to differentiate this thing so that it becomes a constant. So the derivative of that's going to have to be all the way down here. So this is how I do integration by parts. So here we go. Just for completeness' sake, the u is t minus tau, which means the u dash is minus 1. And the v dashed is a half of sine 2 tau, which means the v will be the integral of that. Sine is minus cos, and I'll divide by that 2, so it'll be a quarter by the time it gets there. Okay, cool. Times minus a quarter cos 2 tau from tau equals 0 to t minus the integral from 0 to t of u dashed, which is minus 1, times minus a quarter cos 2 tau. Okay, doing all right. You may notice I've written down that it's tau equals 0 to t, because you can bet your bottom dollar that I would end up subbing the 0 in for t instead of tau, unless I wrote that down. So it's just trying to help myself to not make those sorts of mistakes. Okay, so this bit here will be minus tau times, oh, it doesn't really matter really, tau minus 0, damn it. So minus t minus 0 times a quarter of cos of 0. Oh, that's the bloody hell, David. Stop, slow down. So this thing, the tau is replaced with t. So t minus t cos 2t minus t minus 0 t minus 0, 1/4 of cos 2 times 0. So that's that bit. And then this integral, so the minus would make it just a minus. And I've got a quarter, the cos will become a sine, and I'll divide by 2 again. Okay. And so this bit's 0 because of the t minus t. Cos of 0 is 1, so I've got a minus t, so that's a plus t. Sine of 2t minus an eighth of sine of 2 times 0. So I've got t minus an eighth of sine 2t, apparently. Right. I'm just, sorry? Totally supposed to be a quarter, because it's just here, isn't it? Nice. Well done. Distressingly similar to the just turning it into addition somehow. So I just want to check something. Not that I can do this in the exam, but I just want to check that I've done my convolution correctly. I really shouldn't have done that. So f of x is, well, let's do it with t's. What was it, half? Oh, fun. Okay. So that's the Laplace, that's the convolution, the green one. And so if I write this function, why is that a problem? H of t is, what was it, a quarter of t, minus an eighth of sine 2t, which is so not the same thing. It's pretty close. It could just be something wrong with the way things work here. There we go. It is the same function. Oh, really? Oh, crap. Aha, yep. They're right on top of each other. See, the red bit goes forever and the green bit doesn't. Turn the green off. Yes, okay. I did get it right. Good, good, good. Of course, I can't use Desmos in the exam, sad face, but I trust my skills. So that's what Desmos is for as you study for your exam. It's for helping you believe that you should trust your skills. Because then if you believe in yourself, you'll be more likely to do something rather than just freak out in the exam. So, yeah. Okay. There you go. It seems to me it might have been, I mean, maybe that's marginally slower than the usual method of doing partial fractions. Maybe. Marginally slower, quicker. Maybe it's almost the same as the process of doing partial fractions, but maybe not. The partial fractions process, which is what you'd normally do to do the inverse Laplace transform of this, is possibly a little harder and with more minuses to lose. So, yeah, maybe that's why. But in the end, this semester, doing convolutions is all about doing something that your lecturer asks you to do so that you can finish the course. You know, as much as it's fun to play with these things, it's less fun if you have to be examined on it. So sometimes you just want to make sure you can do what you're asked to do. That's how I felt about Shakespeare in Year 12. Okay. So now we're going to use them to solve a PDE. All right. So I'm just going to have a quick look through the lecture notes that I borrowed. Now, there are all these other things that you can do to Laplace transforms. You can differentiate them, and stuff will happen. And you can sub in t minus something, and that can happen. You can sub in s minus something, and that can do stuff. So it's worth knowing what it does to all of those things, but that's for another day, unless I come back to it, because I want to make sure I have enough time to do all the things that's been asked to do. Okay. So I'm just looking for the classic systems of PDEs. Okay. This is the one I'm going to do from just random place online. So it's different to one of the examples in your lectures so that it's something different. I don't want to do the same ones again. So I'm just going to do it as an example. and we'll see what we can do. So du on dt equals d squared u on dx squared, where u is a function of x and t. It's okay, that's what this says. I think that the brackets xt is just highlighting that this is a function of x and t. Okay, I'm just going to write down all that information. Okay, here it is. Du on dt is d squared u on dx squared. They're curly d's. X is between 0 and 2, t is greater than 0. U of 0, t is 0. U of 2 and t is 0. And u of x and 0 is 3 sine 2 pi of x. Now, this back in Engineering Maths IIA would have been done with separation of variables. And lots of fabulous infinite sums and stuff. And today we're going to do it with Laplace transforms, which is slightly easier. Okay, so what I'm going to do is, I've done an example of this before, and I identified in that example ways to deal with this. So, okay. So first we have to decide, we're going to do the Laplace transform. Definitely we're going to do the Laplace transform, because that's the whole point of learning the Laplace transform. And I can either do the Laplace transform with t as my variable, or I can do the Laplace transform with x as my variable. Considering all our Laplace transforms so far have been with t as our variable, that seems like a good idea. But I just want to be sure. I notice that when I do... Oh, crap. Just a sec. Okay. Well, the example I'm looking for did the Laplace transform with respect to t, which seems reasonable. So I'm going to do that too, but I'm not entirely sure of the reasoning behind that. I guess, well, let's just hope. Just give me a second to read what they did. No, I do not like it. I'm going to do one of the ones. Sorry. Sorry, I don't have enough experience to just pick good examples. So I'm just not going to do that one. Sorry. Ignore that. Okay. I'm just going to run with this. So I have this one, du on dx plus du on dt is x, with u of 0, t equals 0 for t greater than 0, and u of x 0 for x greater than 0. Okay. This may be a simple example, but I might find a better one later. Possibly a past exam question. But I do want to start with this one. Okay. So this is totally almost the same in terms of x and t. But what I can do is it's going to be easier to Laplace transform this x if x is a constant. So I will use t as the variable I normally do it. So what I'm going to do is the Laplace transform sort of t goes to s. That's what I'm going to do first. Okay. All right. And so we're going to let u of s, x and s with a capital U be the Laplace transform of little u of x and t. Okay. So we need to Laplace transform every piece of this, and we can do them separately because they're added. So the Laplace transform of du on dx. Well, du on dx is a function of x and t. And really, if I differentiate with respect to x before or after the transform, it should be the same. And so this is going to still be the derivative of capital U dx. That's one of the rules, apparently. If you've got two variables and you Laplace transform one, then differentiating with the other variable before the Laplace transform is the same as differentiating after the transform. So that's the first thing. And then the Laplace transform of the du on dt. Well, when you differentiate with respect to t, then that multiplies your Laplace transform by s. So it's actually technically multiplying the Laplace transform by x and then subtracting off what it was at the beginning here, just there. So the thing is that we put in f of 0, but my function, it's just the t that we put the 0 in, and the x is still there. So that's the next thing. And luckily, u of x0 is a number. Ah, that's useful to know. So if u of x0 wasn't a plain number, I couldn't do this. It wouldn't be nearly so easy. I could, but if u of x0 was a function of x, I would just put that function of x in this spot. But it would be way easier if it's just a 0, right? Okay, just thinking forward. And then the Laplace transform of just x. Well, x is a constant, so we'll be dividing by s. Because that's how constants work. If I just check that right. Yep. So remember that t is the thing that we're doing the Laplace transform, so the x counts as a constant when we do that Laplace transform. Okay. So now we have that our equation's been turned into something good. Okay, so now we have that du on dx has become du on dx, and du on dt has become su, and the x has become x on s. Cool. So that's linear, right? Okay, so that's a linear differential equation. And this is technically a straight D now. There's no T's in this story at all. No S's in this no t's or s's or anything like that in this story. So I should be able to do this by the same process I do like with an integrating factor, I guess. Or I could, integrating factor is really the same as doing like the constant coefficient like thing. So I guess I'd have to use an integrating factor for that. Okay. Rightio. So this is the variable. And I'd multiply everything through by the e to the integral of that, I think. Yes. It's going to turn to crap, isn't it? I can just tell. No, it's not, because the derivative is with respect to x, so the s counts as a constant. So wait, just a second. Up to this point, the x counted as a constant while we were doing the Laplace transform. So while we were doing the Laplace transform, to get to here, the x was a constant. But from this point forward, when we're doing this differential equation, this differential equation has a derivative with respect to x. And so in this derivative here, the s counts as a constant. That switch is important, I reckon. So integrating factor I is e to the integral of s dx, because this differential equation is a dx differential equation. So if I'm solving it, I'm thinking about dx, and so the s counts as a constant. And so when I do this, all right. So when I do this, like that, magically, that will mean that this thing is already the derivative of this, because that's how integrating factors work. And I'll have to integrate both sides now. Bloody. Integration by parts. Okay, we can do it. Now, if I differentiate the x, it'll go away, so I should do this. So the u is x on s, so that's the same second place. The v dashed is e to the sx, and I have to integrate that. The u dashed is 1 on s, and the v is the integral, which is crap. Let me just do that again. So down here, if I u dash that, the x will go away. So this one has to be the v dashed here. So the u stays the same, so it's still x on s. The v dash got integrated to become v, which is e to the sx on s, because we're integrating with respect to x. And so the s counts as a constant, so we should be dividing by it. Minus u dashed, which is 1 on s, because the x is gone now. E to the sx on s, because that's what this is. And so that's what we have. So when I integrate this, the 1 on s squared from here is still there. The e to the sx will still be there, and I'll have to divide by s again. Okay. And that c, it's not really a c, it might possibly involve an s, I imagine. But anyway. Okay, so x e to the s x on s squared minus e to the s x on s cubed. I feel like I've done something wrong. That's okay? Nope, it's all good. So, my goal was to find out what u was. I mean, the entire goal of this entire exercise is to find out what the function u is. And so, at the moment, I have e to the sx times u is this thing. And so, if I divide by the e to the power of sx, I can get this. Sweet. So in this second section, all of this bit, this was solve the dE that we get, and in this one s is a constant. Okay. Okay. Right. So now we have a formula for what u is in terms of s and x. We're going to have to untransform that, right? But first we need to figure out what the c actually is. Now that c might be a function of s, because when I integrate with respect to x, anything that involves s would disappear if I differentiated, so this might be a function of s, so I might just pop that in. Okay. So let's see. What information can we have? We've used already the fact that u of x 0 is 0, so it seems we need to use this other one, u of 0t equals 0. Okay. Now let's see, u of little u of 0t was 0. So when I do the Laplace transform, I'll get big U of 0s. I reckon. Because the Laplace transform of 0 is still 0. So u of 0s, which is 0 on s squared minus 1 on s cubed plus cs on e to the s times 0 is 0. And so therefore, that's 0, that's 1, cs is actually 1 on s cubed. Cool. Doing well. And so actually, u of is actually x on, bloody hell, s squared minus 1 on s cubed plus that. It seems like a good idea to do this. Okay. Okay, so now the first thing we did is we did the Laplace transform, and during that story the x was a constant. And then we did the solving of the dE, and during that story s was a constant. And we're still doing the solving of the dE. It's just we're finding out what the c is. Okay. So the next question, I guess, this capital U here is actually the Laplace transform of little u, and what we really want is little u, and so we're going to have to inverse transform this. Okay. Right. So again, since we're doing the Laplace transform, which was about S and T, the x's count as constants now. Again, because we're doing the Laplace transform. So we're going to need to look up Laplace transforms for these things. The x counts as a constant. The x counts as a constant. So 1 on s squared becomes t, according to my Laplace transform table. That's the first thing. So just for some colour coding, this bit became this. Okay. 1 on s cubed becomes t squared on 2, according to the table. It says that if you've got 1 on s to the power of n, you go t to the n minus 1 divided by n minus 1 factorial. So this is going to be that. So this bit is here. And that, oh, okay, right, okay. Well, we know what the 1 on s squared becomes. It would normally become the t squared on 2. Right? Doing okay. So, I'm going to just give myself some more space. And we'll do that in a second. Right. Okay. So we know what this is. We know that. That's based on this thing. And there's a thing that if you multiply by e to the something, then you can do something. So where is it? Here it is. Here, if I multiply by e to the minus something s, then I can shift the second shifting theorem. Okay. So, okay. So the second shifting theorem says that if you multiply by e to the minus something s, oh, well, let's just actually write it as something s. Okay, that's what we've got, xs. Then you have the original function at t minus that multiple times, oh crap, well, it's a different u. This is a different u than the other u. This is the unit step. Bloody hell, use the... Stop using the same letter to mean different things. You're just going to have to know that this is a different u. Like this is the Heaviside function, you know, the thing that turns things on and off. What's that called in this course? Sorry? Unit step? Okay. Okay. All right. So that was with the second shifting theorem. Or the S shifting theorem, or the T shifting theorem, or whatever it's called. Okay? And so therefore, u is actually xt minus t squared on 2 plus t minus x squared on 2 u t minus x. And that's the unit step. Ta-da! We feel so satisfied. If I was in a mood and I had time, I would differentiate this to see if it really worked. Yep. So, and sub it back into the original. So I would do du on dx, which is t, that bit's 0, 2t minus x minus that. Ooh, I guess this is 1 after and 0 before. So sometimes it's 0 and sometimes it's 2 of t minus, it's t minus x. Okay. I don't feel like it. But that's how you would check your answer. You'd differentiate it, you'd sub it in and see if it came out to the original derivatives actually did come out to x like they're supposed to. But technically this function is different before x and like if t is less than x and if t is greater than x. Because if t is less than x, this is 0, and if t is more than x, that's 1. So I would have to differentiate it, both versions, yeah, and see if it actually came out to x. I don't feel like it. So I won't. But if I was in the exam, that's what I would do. Unless you make me. Do you want me to do it? Good. At least one person said no. Okay. So the pieces of this are that you're going to have to decide which variable to do the Laplace transform with respect to, and it seems reasonable that you should usually use t. That's like a hint from the person who wrote it. But in this one, it turned out because they were both 0, I could have really chosen either, and that would have probably been fine. It's just that the x would have become an s instead of the t if I'd used the other one. In this other example that I did last year, I chose it based on the fact that that when I sub t into this formula, it comes out to 0, just here. And so when I did this derivative thing, the u of x0 was just a number, and it was a little easier to do my Laplace transform that way. Otherwise, it would have turned out to be a function of t, and everything would have been more complicated. And so that was my decision of which one to do. So, yeah. And then I do the same trick, right? This one was not all that different, actually. So I have to Laplace transform, and while you're doing the Laplace transform, anything that's not t counts as a constant. And then you create a differential equation, which you're going to have to solve using the ordinary methods that we have for solving differential equations, and not using Laplace transforms, because it's just going to turn to pain. So while you're solving that, which may end up needing to be solved using constant coefficient stuff, or possibly it'll just be easy because it'll just be something that you just integrate and you can go, yay, I just integrate it, yay. But it might not. It might have to use integrating factors like I did there. And then you're actually going to have to Laplace transform the other initial condition. So in the one that I did last year, the other initial condition involved a t, and I had to Laplace transform that first. So you're going to need to do that to figure out what the c is. And then you're going to have to un-Laplace transform it. Which may require you to use one of the shifting theorems. Right. So those are the 4 or 5 steps. It's useful for something that's complicated to be able to pull out the pieces of what's happening. So if you find your own worked example from the lecture notes, if you can draw around it which piece is doing what, it's a little easier to keep track of what's happening and to remember it for yourself next time. Right. Thoughts about Laplace transforms? Or questions? Or feelings? Sorry? Despair. That's reasonable. But you do not need to despair. There is hope because we have at least got names for the pieces of this working. So we can remember the bits we have to do. And I hadn't, this is the second year of doing it, and I realized anew that there was, one's a constant in one bit and the other one's a constant in the other bit. That's useful information. So I'm feeling all right. And in past exams, they seem to have the tendency to not require you to do too much fancy integrals because you just don't have time. So that is a nice hope to have. Okay. Well, in that case, I will talk about some multivariable calculus things. Right. Oh, so to answer Saxon's question, who may or may not actually be here. Well, you're watching online. I'm very upset at you for leaving. Actually, just a second. Should have stayed, Saxon. One of the things, he's immortalised on this revision seminar forever now. One of the things that I've been asked is, well, how do you decide what to do? In this one, I knew I had to do a Laplace transform at some point. And so that was one of the things that was guiding me. Say, well, I'm going to have to do it. And I'm probably only going to have to do it once. So the other thing I'm going to have to do is just solve the things that's there. So that helped to guide me on what I had to do, even though I didn't really remember very hard on what was going on. Okay, so we have some things written here. We've got parametric representations of curves, line integrals, double integrals, and changing the order, flux integrals. Okay, that's a lot of the kinds of integrals that we've seen. Does anyone have, feel free to just yell it out all at once, does anyone have a particular preference for any of those things? Gonna have to yell. It's your revision seminar. Or a particular past exam or tute question or something that was hard about these things that you wanted to do. Well, I've got a quick idea. If you interrupt me before I start, if you have something in particular. Okay. I'm going to just talk about some line integrals. So, right. So, when you do integrals, when you first did integrals, the first time you did integrals in your life, there were only line integrals because everything was on the real line, and life was pleasant. I love line integrals in space. I think they're really cool, but the only way to do them is to turn them into ordinary integrals. And so that's one of the big messages. All line integrals must be turned into an ordinary integral first. And that's true for all integrals, actually. So the idea is that you have a function, you have a line, a curve. Do you mean curve integrals? Like just along a, yeah, line, curve, doesn't really matter. You have a line, possibly a curved line, on the plane or in space. And every point in space has a function value attached to it via some sort of function. And you would like to add up all of those function values as you move along that line. So we used to, there's some sort of line like this. And every point has a number attached to it. All right, every point in space has a number attached to it, but in particular, every point on that line has a number attached to it. And what you do is you find some way of keeping track of which point you're up to. So there's some sort of t, a parameter, which tells you where you are on this curve. So maybe this point here at this early t is here, and maybe this point here at a later value of t is here, and maybe this point here at an even later value of t is here. And so what you do is you borrow, you can tell using these values of t what the function value is, and you just redraw those functions as a function. So this number here, you know, there's a number here, and you go, well, that's this height. There's a number here, and that's this height. There's a number here, and that's this height. There's a number here, and that's this height. And together they produce some function, and you do the area of that, and ta-da, that's the answer. You borrow these function values and create a function, and you integrate it, and that's the answer for the line integral. The problem is, it's not quite that simple, because it's the point might be moving faster in some points than others. So as the t moves along here, it may be that it has to go really fast here and really slow here, or really fast in some places than others. So you need to sort of stretch this out. If it's going fast, then those points don't count as much for the integral, because, well, possibly they need to count more because it's going, if it's going fast, if you don't want it to include those you want to include those more because you went past them too quickly to see them. So you need to sort of stretch this in and out a little bit based on how quickly it's going. And so there's an integral thing that you have to do. But this is the basic idea, that these numbers are attached to that, and then you do integrate this. That's this is doing in my head. So all line integrals have to be turned into ordinary integrals via the parameter t. And that's the thing. So as an example, let's have this function. It's x squared minus y. So at every point x, y, there is a value. So when x and y are both 0, the answer is 0. When x is 1 and y is 2, the answer is minus 1. When x is 5 and y is 4, the answer is 21. And every possible combination of x and y that I could think of has an answer for this function. And so I might want to do well, I'm just going to call it f if that's okay. For gamma, it's a straight line from 0, 3 to 1 minus 6. That's what I'm going to do. So this is the question I'm going to do. And the idea is that here is the xy plane. Here is the point 0, 3. And here is the point 1 minus 6. And every point on this curve in inverted commas, this line, has a function value attached to it based on this calculation. So here at 0, 3, the answer is negative 3. Here at 1 minus 6, the answer is 7. And at all the points in between, they all have answers for that. And I would like to add up all those answers based on how long it takes me to go past them. So based on this length here. So that's what I'm going to do. And the only way I can do that, unless I'm using a fancy theorem, is to figure out some number, usually t, which tells me exactly which point of the curve I am up to so that I can track what function value it has. So here we go. On the curve gamma, the point xy is going to be 0, 3. No, I need more space. So I'm going to have to do that. And there are some classic ones you can do. So the classic ones are straight lines and circles. So with a straight line, I think of my straight line as starting at this point and adding a piece of this vector that goes from here to here. So I can say so that vector is end minus beginning, which is 1, negative 9. Okay? And so therefore, the points on the curve gamma are x, y, equals beginning plus some multiple of the vector. And that t is from 0 to 1. We're going to go, well, if we went halfway, the t would be a half. And if we went 3/4 of the way, the t would be 3/4. And if we went the whole way, the t would be 1. So for t in the interval from 0 to 1. That's how to do the parameterization of a straight line. So that's t. If we really want it as a single coordinate thing. Okay, so the only way, so now I'm pretty good. I can write x and y in terms of t, which means I can write this function in terms of t. The only issue we have is that the ds has to be in terms of t as well. Okay, so I know that as I move along this line, if t moves by a little bit, then this point moves by a little bit in that direction. And so what I need to do is I need to figure out what that little bit is, which means I do a derivative. So I can do this. Can I just think about that for a second? Yeah. I'm going to do it as a bold x, if that's okay. Bold x stands for a vector. And I underlined is how you write bold on paper. So that didn't make, that's not going to make any difference. Okay, so dx on dt is 1 and minus 9. So differentiate this with respect to t, this with respect to t, which interestingly is this vector that's attached to the t. So you could actually differentiate it back from here. The thing that doesn't involve t goes to 0, and then the constant attached to the t is the thing there. And then what I can do is I can say that ds, d bold s, which would be a vector move, a vector change in position, would be that vector times dt, and ds would be the length of this. Now what's that? Root 82. Not fun, but just fine. Pretty sure this is right. And so the integral across the curve of f ds is the integral from t going from 0 to 1, because they're the options for 0 to 1, because they're the options for what t is. And the f is really, oh crap, sorry, not ready yet. Getting ahead of myself. Let's just see. Each piece of this needs to be in terms of t. The gamma is turned in from t from 0 to 1. The ds has become this. And the fxy I still need. F is x squared minus y. And the x is really t. And the y is really 3 minus 9t. Beautiful. So now I have all the bits I need to do my integral. So the gamma is being tracked by the t going from 0 to 1. The f is really this. And the ds is really this. Yep, goodo. I was right. Okay. So, I just do the integral. The root 82 can come right out the front. Now, all of those involve a t, so when I sub in t, I'll get, sub in 0, I'll get 0. 1/3 times 1 cubed minus 3 times 1 plus 9 on 2 times 1 squared minus 0 plus 0. And so I get root 82 times whatever this number is. I don't know. 9 and 2 is 4.5, minus 3 would be 1.5, and 1.5 plus 1/3 would be 1 5/6, which would be 11/6. Okay. I mean, that's what calculators are for. So let's do what I said earlier to this to see the pieces that I made of it. So first, I found a way to represent the curve. So I found a parameterization of the curve. That's this bit here. And then I had to find what each of the pieces of this integral were. The first piece was the ds, which is done by differentiating and finding the length of that vector. Find the length of that vector. And the second piece was the f, which I had to sub in the x and y coordinates in terms of t. And the third piece was the gamma, which we did first. So this is dealing with turning the gamma into tracked by a value t. So I'm going to color code. Here we go. This bit is here. This bit is here. And this bit is here. So each piece of my integral I had to turn into something so that I could turn it into an ordinary integral that I could do. And it should come out to a number. It's a definite integral. We're adding up numbers across a line. And you might notice that all of the integrals in this course are definite integrals. Yeah. So the question with some of these things is really about what the parameterization is. So there's straight lines, and straight lines are great, and it's very useful, especially if you're going down the y-axis, to think carefully about this as in your end minus beginning vector like I did here. But circles are common as well. If you go anti-clockwise around a circle, then it's sine theta cos theta. So if you're going clockwise around the circle, then it would be something else. Well, you could always do the theta backwards and do 2 pi minus theta if you wanted to do it backwards. Or if you're going clockwise, you can go cos theta sine theta, and that would come from here and go that way instead. Crap, it is backwards. They're supposed to be in alphabetical order, people. Right. Cos is before sine because they're in alphabetical order. Okay. If you had done sine theta cos theta, it would have been going this way from the top. Right. I'm glad I mentioned that, or I wouldn't have noticed. Okay. And if you've only got a piece of the circle, you just use a piece of the angles. So there was one in the assignments this semester which had just a quarter of a circle. And so you went from 0 to pi on 2 for that piece. And if you have something that's made up of several different pieces, one bit's a circle, one bit's a straight line, then you're going to have to do each bit separately and add them up afterwards. Yeah. So I was asked about sanity checks somewhere in the room. Yeah. So asked about sanity checks. I'm just going to see if this seems like a reasonable answer for this thing. Well, it's a straight line. The area should sort of be like whatever this is on average from here to here. Right, the average value of something times the length that you go across should be should be what the area is. And so the length of this, we already figured out, that was the root 81. So that's seeming to tell me that x squared minus y should be 11 over 6 on average across this line here. And I guess that sort of the x is going from 0 to 1, so that on average is a half. And the y is going from 3 to minus 6, so that on average is, what's 3? From 3 to minus 6, that's add them together, that would be minus 3. That on average is minus 1.5. And a half squared is about a quarter plus 1.5. Yeah, it's not too bad. That's actually pretty good. Because we got a 1.5 plus a third, didn't we? So it's a pretty good idea. So the average value of the x and the y subbed into this was not too bad an estimate for the average value of the whole function. So it seems all right. It's not too bad. It's about the right size. Most of these numbers are pretty small. So that's a guess. Okay. So what about, is a flux integral an integral across a surface of a vector? I can never remember what that's called because it's called something different in different courses. I am looking for the word flux. It would be easier if I had an electronic version. Flux integrals. A vector field through a surface. Okay, cool. Okay, so there's two kinds of surface integrals in this course. And that's because there are two kinds of functions in this course. There are vector fields, which at every point in space produce a vector, and there are scalar fields which at every point in space produce a scalar. And so therefore we have two kinds of integrals. One where we're integrating a scalar, one where we're integrating a vector. And the one where you're integrating a vector is called a flux integral. So, apparently. So you integrate a vector across a surface. Okay. Now, here's the thing. This is how I would normally write it. So the thing about this is that you can't really integrate vectors. You can only integrate numbers. And so the only way to integrate, in inverted commas, a vector is to turn it into a number somehow. And the way that we do that is with this dot product just here. That's why we write it as a dot product, so it turns my vectors into numbers. So when you integrate a vector across a surface, what you're going to do is you're going to create at every point on the surface a vector which indicates which direction the surface is pointing at the moment, like what's perpendicular to the surface. And you are going to find how much of this vector is in the same direction as the surface, and then you go, and that will be a number, and that's the number you're going to add it up across the surface. There you go. So there are two ways to do it. One is to just do it, which means we have to create a double integral in terms of two variables and integrate across both of those variables. And the other way is to use a fancy theorem that turns this into a different kind of integral that might be easier. But usually this one's the easier one, actually, compared to the other one that we would turn it into. So, yeah. So, in my head, I think of it this way. So normally, that's a big S, by the way. It's a capital S. So back when we were doing curves, ds was a little tiny piece of movement along the curve. Well, when you're doing a surface, d capital S is the cross product of a little tiny movement in both directions along the surface. So the idea is that you've got a surface which looks like whatever it looks like. And if you go a little bit this way and a little bit this way, their cross product is ds. That's the idea. Okay, so normally what you have to do is you have to do give me a second. Oh wow, that is not at all described. Okay, right. Normally you figure out what position you are on the surface, and you find two variables u and v which describe which point on the surface you're on. And you differentiate with respect to both of those things. That's my understanding of that. So parameterize, this is the point x on the surface, and u and v tell you which one you have, and you differentiate with respect to u, and you differentiate with respect to v, and you cross product them, and then that is what ds is. Works better in an example. Where, let's see, S is the top half of that sphere. X squared plus y squared plus z squared equals 4. And f is of x, y, z is x plus y. Let's do that. Just a random example I pulled out of my head. So first, the only way to do an integral is to figure out what every point... Actually, I can do this one a different way, but I'll get there. The only way to do an integral is to pick out some sort of coordinates that tell you what every point on the surface is. So if I have a sphere of radius 2, because that's what this 4 is, okay, that's a number 2, like that. I need to figure out a way to find every point on this surface. So, there's a classic way of doing this for spheres. I always forget it. Certainly there's lots of circles involved here. There's, I could cut this into a whole lot of circles based on the horizontal location, and those circles could be done as cos theta sine theta. So I can have for the x something cos theta and the y something sine theta, but it depends on something to tell me what the radius of that circle is. Let me just draw it again. How am I going to figure out what the radius of that circle is based on a number? We've got a theta to say how far round the circle I am. Ooh, okay, cool. What if there was an angle here, phi, because then the height would be sine, the radius is 2, and the height would be 2 sine phi, and the cos would be 2 cos phi. The bottom, which is the radius of this circle, would be 2 cos phi. Got it. Okay. So we have circle radius cos phi, 2 cos phi at height 2 sine phi. And so therefore it's got this radius, cos theta, this radius, sine theta, and the height is this height. That is every point on this sphere. And the phi is going to go from 0 to 2 pi because it's tracking upwards like that. And the theta is going to go, not 2 pi, from 0 to pi on 2. And the theta is going to go from 0 to 2 pi because it's going round this circle. Okay, I believe your lecturer is probably going to give you that parameterization rather than making you figure it out yourself. That's the sort of person he seems to be based on past experience. So, yeah. But that is how I figure out a parameterization. Okay. So what you would do is once you've got the parameterization, I need to turn everything into something in terms of these two parameters, which in the earlier story I called u and v, but today I'm calling phi and theta. So let me just check something. I'll figure that out in a second. The derivative of x with respect to phi is, that would become a minus 2 sine phi, and the cos theta is a constant, so it's still there. Minus 2, and that's 2 cos phi. And the x theta is the 2 cos phi is a constant, and the cos theta becomes sine theta. The 2 cos phi is a constant, and the sine theta becomes cos theta. The 2 sine phi is a constant, so that's 0. So they are the two derivatives, and I need to cross product them to get things in the correct direction. I'm going to have to cross product them so that the vector points outwards. So let's just try this. If the theta is going round that way, so that means it's pointing that way. The phi as I move up is going to go that way. So theta cross phi is going to go inwards. So we actually need to do the phi cross the theta. No, it's the thumb first, isn't it? So theta goes that way. Yep, it's going to go inwards. So I need to go phi, which is going up. No, that's inwards. Theta, phi, right, it's the correct way round. There's a sphere here. Theta's going that way, phi's going that way. If I do the theta first and then the phi, my hand's pointing outwards. The cross product points away from the sphere, which is the one we want. So we want to go theta and then phi. Okay, so to do a cross product, the cross product in the first coordinate I have this times this minus this times this. Is it? Well, which bit am I pointing at? All right. So this times this minus this times this, which is that. And then the middle one is minus this times this plus this times this. And the last one is this times this minus this times this, which there's a lot going on there. So we've got minus 4 sine phi cos theta squared minus 4 sine phi cos phi sine theta squared. Wow. Okay, sure, and why not? Oh no, this isn't a 2, that's a 4 as well. Okay. Okay. Right. Well, this is thing cos squared and another same thing sine squared. So cos squared plus sine squared is 1. All right, and I guess the minus 4 cos phi can come out, I suppose. I do not like it, Sam, I am. Did I give myself a function? Oh, it can't be x plus y, it's a vector function. Oh, for the sake of Frel. Let's call it x plus y 0, 0. Because that's better. Okay. Nearly there. So f of x, y, z is 2 cos theta cos phi cos theta plus 2 cos phi sine theta 0, 0. Yep. Whoa. My fault for choosing something bad. And then I have to dot them together. I won't put the integral in yet. So f is this, and ds is this dot d theta d phi. So I've got so when I dot product them, the zeros go away, and I get whatever that is. So this times that is 2 cos phi squared cos theta squared, and this times that. Crap, I don't care. Right, I'm feeling a little bit overwhelmed here. Okay. That I have to integrate, and I don't feel like it. It's bad. Okay, and so the integral will be this. So the theta goes from 0 to 2 pi, the phi goes from 0 to pi on 2. This we put here, d theta d phi. And I do not want to integrate that. Oh, crap. So this thing here goes here. So there's no, I mean, it's not pretty. And I do not enjoy the prospect of actually integrating that. This is the sort of thing that if I was in my exam, I would just leave it there. So, right? And even better, I would check to see if the lecturer said, write an expression for, and I'd go, yes, they did. Good. I don't have to do anything else. That's just hoping that they were nice. I could have tried to do this another way via a path integral or something by using Stokes' theorem or something. Or if my vector happened to be perpendicular to my surface all the time, or if I happen to know a vector that was perpendicular to my surface all the time, I could possibly turn it into something that used the volume of a sphere. But it's not going to work today. There are other examples online that I've done which are better because I was better prepared. But that's where I'm going to leave it. The big idea for all of this for me is that those pieces that have to go together, that in just like a substitution, when you did substitution back in Maths 1A or even in high school, where each piece of the integral has to be turned from x to u, same as in this, each piece of the integral has to be turned from vague thing involving x, y's and z's to something involving the parameters that parameterize your surface. And I find that the easiest way to keep track of everything I have to do in order to actually do the calculation. Yes. All right. Thank you. Good luck. Maths Learning Centre is open. Of course, you know, first year's first and all that. But the first years have all their revision seminars tomorrow. So just worth knowing that. So, yeah. Do you still have an assignment to go? Like a map or TA? Yeah. All right. Yes. Good luck. And don't forget there's other revision seminars out over there to have a look at.